Hi everybody, welcome to the section 4.3 video. In this video, we're going to be taking a look at constant coefficient homogeneous differential equations. So in this section, we're going to be able to define what a constant coefficient homogeneous differential equation is. We're going to solve these differential equations with three specific cases, one being unique real roots, two being repeated roots, and three complex roots. And then we'll tie it all together by solving an initial value problem of these constant coefficient homogeneous DEs. So let's introduce a bit what constant coefficient DEs are. So in the previous section, we were finally introduced to second order or higher homogeneous and non-homogeneous differential equations and their respective solutions to each one. So in this section, we're going to be focusing on just homogeneous differential equations. That's our focus here. And specifically, we are going to be going over homogeneous differential equations that have constant coefficients. Constant coefficients meaning numbers. So within this method, we were solving a homogeneous DE and just a homogeneous component of a general solution. So we are focusing on getting this complementary part, YC, of a differential equation. So a complementary solution. We're obtaining this component right now, the homogeneous part, but we'll get more on that next section of how to deal with the non-homogeneous part. But we're focusing on the homogeneous part now. So let's define what a constant coefficient homogeneous DE is. So a second order, we're in second order land now. Homogeneous differential equation is of this form. A times y double prime plus b times y prime plus cy equals 0. And so notice that a, b, and c are all real numbers and are the constant coefficients. So whatever is attached to our variable and derivatives, y prime, y double prime, those are constant coefficients. And so our goal is to solve any problem that looks like this, a constant coefficient homogeneous differential equation. So how do we go about solving one of these differential equations? Let's see. So consider the general homogeneous constant coefficient differential equation. Let us try and solve. So trust me, and let's take a guess that y equals e to the mx is a solution. Trust me on that, and let's see what happens. So if I'm saying it's a solution, and I want to verify it's a solution, so I need to plug it into this differential equation. So there's a couple of things I need. I need its first derivative, and I need its second derivative. So its first derivative, using the chain rule, is m times e to the mx, and its second derivative, using the chain rule again, is m squared times e to the mx. And so what we're going to do is take these and plug in to the differential equation and verify it. So I would have a times m squared e to the mx plus b times m e to the mx plus c times e to the mx equals 0. And so let's clean this up a bit. Get rid of these parentheses. We have a m squared e to the mx, b m e to the mx plus c e to the mx equals 0. Okay, so one thing they all have in common is this e to the mx. So I'm going to factor out an e to the mx. So I'm just left inside am squared plus bm plus c equals 0. Okay, so both of these components equal 0, but let's pay attention to a couple things. That an exponential function never equals 0. It never equals 0. So that means am squared plus bm plus c must equal 0. And so this expression right here, this quadratic formula, is what's known as our auxiliary equation. And that's what we're going to be using, excuse me, auxiliary. And that's what we're going to be using to find our constant coefficients from a differential equation of this form. So to kind of summarize, y equals e to the mx is a solution when m is a root of the auxiliary equation. So we're going to use this auxiliary equation and we're going to be able to find our constant coefficients. And so that's it for this video. This is a nice introduction to our topic, and we're going to try out some examples in the coming videos. Okay, thank you for watching, and I'll see you in the next one.